Okay, so yeah, thanks, David. Welcome to the first GeoTalk. I'm going to be talking about iceberg armadas in the geological past. So this is work that we've been working on in our research group at Cardiff with various collaborators, focusing on the kind of paleoclimate picture of icebergs, particularly in the Southern Ocean, and how this can inform our understanding of the climate system, with obvious implications for how we understand that system as we move forward. Yeah, David's kind of covered all of the housekeeping. I've put the next 3 talks up on here, and the full program's available on the website. I'll talk for about 20 minutes, and then there'll be time for some questions if any appear. So feel free to drop a question in the Q&A box if and when they come to you. So to get started, a quick outline. The talk will be in 3 parts. So I'll start by talking about modern icebergs, a little bit about the basics, and then we'll move into icebergs of the past, particularly Antarctic icebergs. And then we'll bring this together and see how this is kind of culminating in an emerging hypothesis that we're working on at the moment. And you can find me on Twitter or drop me an email if you want more info. So the real basics, starting right from the start. Icebergs, they are floating masses of freshwater. So freshwater ice which have broken off of glaciers into the ocean. So in Antarctica, snow and ice accumulate on the continent, so it snows and it gains mass. This gain of mass is balanced by a loss of mass at the edges of the continent. So through the carving of icebergs into the ocean, for example, and by basal melting at the base of the ice sheet. In our research, we're particularly interested in the life after carving. So what happens to these icebergs after they've broken free into the ocean? And as I said, particularly, I'm interested in the Southern Ocean. That being said, much of the research into icebergs historically has been focusing on the North Atlantic. And this makes good sense. If you think in 1912, after the sinking of the Titanic, the IIP, the International Ice Patrol, was set up. The idea being that they could monitor the position and movement of icebergs in the North Atlantic. However, we have got evidence and there are historical documents that all through the late 19th and 20th century have sightings of icebergs by ships in the Southern Ocean. There's a really interesting letter to the Quarterly Journal of the Royal Met Society in 1910 with a report of numerous sightings of icebergs all over the mid-latitude Southern Ocean, more than one of these ending in collision. Some of it's quite harrowing reading. One of the most remarkable reportings was in 1894, a Scottish ship named the Docra were reported spotting a remnant of an iceberg 4 foot high. And what's remarkable here is the sighting was made at 26 degrees south off the coast of South America. That's roughly the same latitude as the capital of Mozambique. So it's an extraordinarily warm iceberg. It's made its way thousands of kilometers away from Antarctica. And this is, in the satellite age, we don't really see this. We don't see icebergs making it this far. But I've added here just a collection of the shipboard observations from the late 1800s with pictures of the ships that made the observations. We can see that from shipboard data, we build a relatively kind of sparse database of where icebergs might be. It's not overly helpful if we're trying to understand the kind of physics behind the iceberg trajectories. And so the onset of the satellite age really vastly improved our understanding of the path that icebergs follow once they've left Antarctica. So the life after carving of an iceberg, we can see from this plot from freely available satellite data of iceberg trajectories. Once the icebergs leave Antarctica, there is order to the path that they follow. So generally they'll follow a counterclockwise route around the continent, and then they'll fly off the Antarctic Peninsula into the South Atlantic. And this starts to make more sense if we overlay the surface circulation in the region. So we can see that the icebergs initially are following the Antarctic coastal current, and then once they reach the Antarctic Peninsula, they fly off into the South Atlantic and join the Antarctic circumpolar current. So this is good. We can build an understanding of the physics behind these iceberg trajectories. However, satellite records go back to the late 70s at a push. Really well-documented shipboard records, the earliest I could find was the late 1700s. But as a paleoclimate scientist, I'm really interested in slightly further back in time than the 1700s, particularly, for example, if we're interested in the Pleistocene, which I am, which is 14,000 to about 2.5 million years ago. And this brings us on to part 2 of the talk, which is Antarctic icebergs of the past. So it's one thing to be able to understand icebergs in the modern ocean. However, over the last, say, 60 million years, as a climate scientist, we can look at this and think of these different time periods as kind of natural experiments, natural climate experiments. So we have this huge variety of natural climate variability associated with different forcing. So we have changes in the way that Earth orbits around the sun, fluctuations in the level of atmospheric CO2. We have the growing of ice sheets, the collapsing of ice sheets. We have all of these different varying states. And what really interests me in particular in my research is how the Southern Ocean, how ocean circulation and how Antarctic icebergs behaved under these different conditions. So the middle panel here is the Pleistocene. This is the period of time that I focus on in my work. So the question arises, if we can't use satellites, obviously, we can't use shipboard records, how do we reconstruct the trajectories of icebergs in the geological past? And anyone who reads a lot of Agatha Christie might tell you that an icicle is the perfect murder weapon, leaving no trace behind once it's melted. Luckily for us, the same isn't true for icebergs. So when icebergs melt, they do leave a trace behind. And this is because in icebergs, you tend to get lots of tiny fragments of rock and sand and gravel and mud forming in these bands of debris. And I get to share some photos from my favorite ever academic paper, which is Anderson in 1980 in the Journal of Glaciology. It's definitely in a time before the sort of health and safety that we're familiar with. They flew a helicopter to some of the dirty Antarctic icebergs that they spotted from a ship and climbed aboard and hacked off chunks of the iceberg to understand what was actually what made up the ice. And as you can see from this photo, loads of layers of rock and debris in these icebergs. So this is really useful to us as paleoclimatologists, as it kind of tells us about the past life of the iceberg. So before the iceberg carved from the ice sheet, it was part of a flowing ice sheet. And as these ice sheets flow, there are various ways that they can pick up rock material from their source area. So as the base of the ice sheet kind of melts and freezes again, it picks up sand and gravel from the bedrock underneath. You have supraglacial debris, so gravel from, say, up in the Antarctic mountains. You have dust as well settling on top of the ice sheet. And all of this gets kind of frozen into this kind of microcosm in the iceberg. And you have this picture of where the ice originated, this signature, this character stored in the ice. When the iceberg flows into the open ocean, it starts to melt, it encounters warm water, and these tiny rock fragments get dropped and they end up accumulating in the layers of mud on the sea floor. So we call these fragments ice rafted debris, or IRD, and we can go and look up deep ocean mud and we can look for these layers of ice rafted debris. This means that we have to go to sea sometimes and extract cores of sediment. So on the left, we've got two of the kind of famous research vessels used for recovering sediment cores, the French Marion Dufresne and the American Ploides Resolution. And on the right, we've got two photos from two different expeditions where we were recovering deep sea sediment from the Indian Ocean and the South Atlantic Ocean. And the principle here is relatively straightforward. If we take a core of sediment, the sediment at the top of that core is going to be younger, it's going to have been deposited more recently than the sediment at the bottom of that core. So in this example from the Indian Ocean, we found the top of the core was roughly modern. So this is sediment that is kind of being deposited over the last kind of few thousand years. This brown layer, about 50 centimeters down, we identify as the last ice age, so about 20,000 years ago. And then at the base of the core, we reach about 120,000 years. So this is the kind of principle of sediment cores in it. It means in each of these layers, we have an archive where we can reconstruct what the conditions were like when that mud was deposited. And if we're lucky, when we bring these cores out of the ocean, we might find evidence for iceberg presence in the past. So this is from an expedition in February to the South Atlantic Ocean. We brought this core up and opened the core in half, and we see this beautiful chunk of Antarctica sitting in the mud. And they're not usually this obvious. And the beautiful thing is, in this big fragment of IRD, you can see the scratch marks and the striations from when that rock was being ground up in the ice sheet. When it was kind of being transported in the glacier, it's getting rubbed against other rocks, and these really characteristic scratches appear. So this is how we build a sort of geological evidence for icebergs in the past. And the example I'll talk about is from the International Ocean Discovery Program site U1475. And this is a long sediment core, which most of my research focuses on. And it was recovered in 2016 from about 450 nautical miles south of Africa. It's about 7 million years of sediment. And we can see from this map that in the modern ocean, it's not directly under the trajectories of any Antarctic icebergs. It's quite a long way from the main Antarctic iceberg belt in the South Atlantic. So the yellow star is the sediment core location. And what we see is actually, as we work through the sediment, we start to find evidence that actually at different times in the past, there were icebergs present at this location. And so in the photo I showed a second ago, we have this big chunk of Antarctica. At U1475, the fragments aren't so obvious. So we have to sample the mud. First, we'll look under a light microscope or a binocular microscope, and we start to identify different mineral grains, different rock fragments. Then we can make use of the scanning electron microscope in Cardiff, where we get to have a real close-up look at the grains, and it can also to give us a kind of chemical signature, chemical composition of each of the grains. So we take the mud, we extract some of the grains that we identify as probably coming from past icebergs, and we put them in a scanning electron microscope. So here's an image of a quartz grain from this sediment core, and this was exactly what we were looking for. We see those trademark striations, those scratch marks on the quartz grain, these conchoidal fractures that indicate that there's a good chance that this at some point underwent some kind of glacial erosion. And as I said, we also get an idea for the chemistry. So if you remember from the photo of what the grains look like under a light microscope, it's incredibly difficult to identify them as different minerals. Very skilled. So one of my supervisors claims that she can by eye differentiate these different clear mineral grains, but I'm not there yet. So this gives us a really nice way of identifying what the grains actually are. And so from this site, we have mostly quartz, we have some garnet, and we have some potassium feldspar. Now, what can this tell us? What additional information can this tell us as we're kind of building this picture of past icebergs? Well, it tells me that there's the source region has some kind of continental crust geology. So if you can see from this kind of simplified geological map, the islands in the South Atlantic here, the purple hexagons, tend to have a more volcanic geology. They're volcanic islands. So if the ice was coming from this region, we would expect the ice rafted debris to be full of volcanic glass and ash. Similarly for Patagonia and the Antarctic Peninsula, we would assume we would have a more basaltic composition. However, what we see, this kind of mostly quartz with garnet, is quite similar to the sediment that we find right at the mouth of glaciers in East Antarctica and in the Weddell Sea region of Antarctica. So from this single site off the coast of Africa, we know that there were times in the past when icebergs from this far over in Antarctica in the Weddell Sea were surviving this long journey across the Atlantic all the way to this region off the coast of Africa. And if we look in a temporal sense, if we count these grains in each sample, so let's say in every 1,000 years, if we count how many of the grains we see, we start to get an idea for iceberg presence at different times over the past 1.5 million years. So we can see that in the modern day, which is kind of 0,000 years before present, we don't really have any deposition of IRD. This makes sense with what we saw in the satellite image. We don't really get icebergs surviving that far. However, as we move back in time, we've got periods where we have almost 600 grains of IRD in every gram of sediment deposited over 1,000 years. And what this can tell us is that there are certain climate conditions where icebergs do survive much further into the Southern Ocean. And what I've done here is highlighted some of the key kind of ice ages of this time interval. So we can use a second paleoclimate proxy, which is the oxygen isotope composition of tiny fossils we find in the same sediment layers. And we can see that at times when ice rafted debris is very high, the 18O, the oxygen isotope, is very heavy, which means there's a higher global ice volume. There's more ice on the planet. So we see that in ice ages, we have more IRD at the Agulhas Plateau at site U1475. And all of this together starts to culminate, and we can start to put together our hypothesis. The question now is, how do we go from this kind of single location, this one geological record, and how do we extrapolate that to improve our understanding of the climate system and of the ocean system? So in glacial periods, there's more icebergs. These icebergs appear to have originated near Antarctica in the Weddell Sea. One way that we can utilize this information and really kind of squeeze as much extra information out of it as we can is to use that data to inform and run numerical model experiments. So one of the beautiful things about having these great satellite records in the modern ocean is that we can get a really good idea of the forces that govern the drift of icebergs in the open ocean. And I won't go into the maths of this equation, but essentially what we have is that we can model an iceberg. We know which forces act on it and in which way they act. And we can run models where under different climate conditions, we see where the icebergs end up drifting. So this is work that we applied to this example. And we can see here from 2 experiments that we ran, we dropped 100 icebergs into this box, which we call the iceberg seeding region. This is to kind of simplify things a little bit. We saw from the satellite that most of the icebergs that enter the ocean all the way around the coast of Antarctica here tend to pass through this, it's called Iceberg Alley. They tend to pass off through this area on the coast of the Antarctic Peninsula. So we drop 100 icebergs there, and then we let 1,000 years happen with ocean conditions from a general circulation model, and we see where the icebergs end up. And when we configure the model to be in pre-industrial conditions, so essentially modern conditions, which is the pink line here, we see that icebergs very rarely survive to the site U1475, to the Agulhas Plateau. If we tweak the conditions in the ocean model to represent more of an ice age condition, so if we use the orbital configuration and the CO2 forcing from the last ice age, we see we have many more icebergs surviving from Antarctica all the way to just off the coast of South Africa. So why is this important? Why do we, aside from this being, in my opinion, quite an interesting exercise, what does this actually mean for our understanding of the ocean climate system? So in this plot here, we can see that from those 2 experiments, we can plot where the meltwater of those icebergs ends up. Once that ice melts, that's a big load of Antarctic fresh water being dumped in the otherwise salty ocean. In the pre-industrial condition, most of that iceberg melt happens south of 50 degrees south, so relatively close to the Antarctic continent. In the glacial conditions, most of that melt actually shifts to the north and ends up in what we call the subantarctic region. So we suddenly have all of this fresh water, gigatons of fresh water being dumped in the subantarctic region, slightly further away from the coast of Antarctica. And yeah, why is this important for ocean circulation? Well, salt water is heavier than fresh water. So if you add fresh water to the ocean, it's going to be much less dense than the salt water that would lie underneath it. This is one of the key principles in our understanding of large-scale ocean circulation. So this is a cross-section view of what we call the meridional overturning circulation in the modern ocean. Essentially, we have water that comes to the surface near Antarctica, and it gets less dense because of what it cools, and also as sea ice forms, the sea ice leaves behind salt. So when seawater turns into sea ice, it doesn't take the salt with it, it leaves it in the water behind it. This makes the water mass very dense, which allows it to sink right to the bottom of the ocean. Now in this plot, we see oxygen, and the high oxygen values of this water mass, this deep water mass, tell you that it's had a lot of communication with the atmosphere before it sank. And if it's very good at taking oxygen from the atmosphere and storing it in the deep ocean, it means it's probably very good at taking carbon dioxide from the atmosphere and storing it in the deep ocean. So what does this mean for our experiment, for our glacial conditions? It means that in glacial periods, Antarctic iceberg melt moved further to the north, which means fresh water that would otherwise be added close to the continent where these deep water mass forms, which are very good at storing CO2. Instead, the fresh water is taken away from the continent and doesn't negatively affect the buoyancy and the densification of that deep water. So ultimately the shifting, and this is our emerging hypothesis, I should say, the shifting band of where that meltwater ends up can ultimately modify how much carbon dioxide is stored in the deep ocean. And this answers a question that has been kind of puzzling us paleoclimatologists for a while. We have evidence that the glacial ocean circulation was very different to the modern, but trying to understand why has been somewhat of a mystery. And this is one potential explanation for how you get this much larger reservoir of high CO2 Antarctic deep water masses. So yeah, in our hypothesis, it's all thanks to the icebergs. It's all thanks to the shift in where the icebergs turn up. So thanks for listening. The paper currently in review is Antarctic Iceberg Melt Driver of Glacial Deep Water Mass Reorganizations, if you're interested in finding out more. And I have to say thanks to the Natural Environmental Research Council, IODP and Cardiff University for facilitating the research. Thanks.
Thanks a lot, Aidan, for that very interesting talk. I think we can go straight to the question. So I can read the questions, and if you're happy, you can try to address them. There was the first question by Nishi here. She was wondering how we decide upon the location where to get a core drilled, because she says it's rather difficult, or it seems difficult to delineate the track of the icebergs.
Yeah, so it's a great question, and in the Southern Ocean, particularly, trying to find a location where you have good mud that has been deposited in a linear fashion, hasn't been ruined by strong currents and hasn't been churned up by worms, and it's actually really difficult. That Antarctic circumpolar current I labeled is a really powerful current, and a lot of the sediment that usually would be deposited in the Southern Ocean is picked up again by the Antarctic circumpolar current and thrown all over the place. So it's a case of finding any location where there's lots of good sediment accumulating in a nice kind of pleasant way. So we're kind of a slave to where we can find good sediment records.
Thanks. I think that addresses the question. Another one is about the sea level. Will changes in sea level affect the migration routes?
Yeah, that's a really good question as well. It's so in terms of the future, like I assume this means that changes in sea level in the kind of future. It's very difficult to say, and using these models is one way that we can sort of understand the response of iceberg trajectories. So for example, the winds might shift and get stronger, which would likely move the trajectories further north. Then again, it gets warmer, so they don't survive so far. The sea level itself, the only real effect I can think that would have would be on the production of new icebergs, so the carving of icebergs from the glaciers. Most of the actual ocean, the open ocean, is way too deep for the icebergs to be too worried about how much water is underneath. But there are regions where the icebergs end up getting grounded. Perhaps we would see more grounding of icebergs with, or less grounding of icebergs, sorry, with increased sea level and vice versa.
Great, thanks, Aidan. I don't think there are any other questions, so the people still with us, I think most of the participants are still with us actually, which is great. If you want to ask a question, I think that's about the right time. In the meantime, I just wanted to say we're trying to record that seminar, and hopefully we can upload the seminars on our Facebook page. So if you cannot make it during one of our forthcoming events, hopefully you can still catch up just looking at our Facebook page. The information is going to be, if we can do this, we're going to post the information on our webpage with all the information about the program and the link to access the Zoom sessions. So it looks like there is no other question. So thank you again, Aidan. I think it was a very interesting talk. So next week, we're going to change a little bit the topic. We're going to talk about earthquakes. It's going to be a talk by Dr. Ake Fagrang. We're still going to be a bit in the ocean, but we're going to look at slightly different processes. In the meantime, I hope you make the most out of the very nice weather, and hopefully you can join us again next week. Thank you all, and hopefully we'll see you again next week. Bye.
Thanks. Bye.